This presentation was originally scheduled for a session on the history of operations research. The story of how linear programming became practical starts in 1948 with this paper by George Danzig. As far as I know, this is the first place where the term linear programming appeared in print. Danzig had originally called it programming in a linear structure. The paper is concerned with modeling, so it has a lot to say about formulations and various applications, but it does not really talk about algorithms. There is one paragraph, however, that says that it is proposed to solve linear programming problems by means of computers, and there is active research in this field. And sure enough, the next year, we see another paper by Danzig. And this is the first paper, as far as I know, where the term simplex method appears in print. And Danzig, again, shares the credit for coming up with this term. And this paper offers a full description of the simplex method and the proof of convergence on linear programs with some reasonable non-degeneracy assumptions, but there is no computation in it. Except there is one paragraph that does say that makes some comments about practical computing and the fact that, well, this method should not seem to be as expensive as it might appear. And so already people were thinking about computing, and within just a few years, the idea of solving linear programs had been established. And in 1953, we see this textbook on linear programming. And the work here of Cooper and Charnes is, as far as I know, the first place that the term simplex tableau appears in print. And they describe the simplex tableau as a way of conveniently arranging the data for purposes of computation. And they also disclaim credit and give the credit to Orden, Danzig, and Hoffman. This paper has a symbolic description of linear programs and numerical examples of solving them using simplex tableaus. But although this showed a full example of how to solve linear programs, linear programming was not practical at this point. And to set the sort of the foundation for that, I have a few slides of notation. The only things I really want to point out on here are that there are M constraints and N variables. Okay? And there are sets of basic and non-basic variables. The basic ones are M basic ones and N minus M non-basic ones. And if you take just the basic ones, you get a square matrix B, which is called the basis matrix. So in terms of this, the tableau method, the main things to know about the tableau method are first that it sets up this big table that's roughly M plus 1 by N plus 1, or rather M plus 1 by N minus M plus 1. And so if you have like 100 constraints and 400 variables, then this is a 100 by 300 table of numbers. And there's actually one extra row and one extra column added to that. So you have this big table that you need to set up. And then if you look at all the computations involved here, the main one is this pivot, which involves subtracting a multiple of one row of this big table from all the other rows. So that dominates the work. So now we can ask, well, why is this impractical? And why is this not a practical simplex method? Well, partly there are just too many numbers. Okay? There are M times N minus M additions and multiplications at every step. And then you have to write and store all these numbers. Okay? And on the computers of the time, this was going to be pretty impractical even for smallish problems. 100 constraints and 400 variables, it would be like 30,000 numbers. And additionally, less well known, this was not a particularly numerically stable method. There are very fixed rules for choosing the pivot element, which in this formula, the element of that big tableau that's in the denominator. And it can happen that this number is rather small, and then it's well known that this sort of elimination step that you do on the tableau, when this number is small, you can get serious loss of precision. So basically, this method did not lend itself to adapting it to concerns about numerical stability. So linear programming was not practical at this point, but within a year it had become practical, and we can see that by looking at the progress in 3 technical reports that were written then. Okay? So the first one by Danzig, Orton, and Wolf is about an improvement to the simplex method. But the improvement they had in mind was the so-called lexicographic simplex method, which was a special simplex method for preventing cycling due to degeneracy in the basic solutions. And this lexicographic idea never really made it into practical implementations. It turned out not to be so necessary. However, it did also involve adapting the computations in order to make them reasonable. And it turned out that those adaptations were of interest in their own right. And so there was already, you can see in statements in this paper, there was already concern about making the computations more practical. And this was followed up in another paper by Danzig right after that. And this paper introduced the term revised simplex method. And here was the first example of coming up with a different version of the method that would seem more practical. And in this method, the tableau table is replaced by just the basis inverse. So instead of having as I said, like a 101 by 301 table, you'd have only a 100 by 100 table. Okay? And the computations were streamlined in consideration of this. Okay? And here we see the paper talking directly about important advantages of the new method over the old one. And mainly Danzig had in mind 2 kinds of advantages. Okay? But let me just show the method here. It looks very much like the tableau method, except instead of the y's here, which were the elements of the tableau table, there are the z's, which are the elements of the basis inverse. Right? The update is a pivot just like before, and some of the computations are different. Some things that were in the tableau are now computed as needed. Okay? And so what did Danzig see as the advantages? Well, there was a smaller update, as I said, you use now just this square basis inverse, which is square by the number of constraints, regardless of the number of variables. Okay? And the other thing was that when you computed these numbers that you needed, they were computed in terms of the original data, which tended to have a lot of zeros in it and made it possible to do this more efficiently. And you didn't carry all these numbers in the tableau. Okay? However, the impracticalities were exactly the same as for the tableau method. Okay? There was still this table. It was a smaller table, but still a big table of numbers, 10,000 in my example, that had to be added, multiplied, and written and stored. And the numerical instability concerns were exactly the same. So we still didn't quite have a practical simplex method. But if you return to that quote that I had from Danzig about how it required only m squared elements, I actually left out a bit at the end. He said also, and an alternative method can reduce this to m. So actually there was a more efficient method that they had in mind, but just wasn't presented in this paper. It's in the 3rd paper of the series. Okay? And that's this paper here. Okay? And in this paper, for the first time, we see Danzig and Orchard Hayes. And up till now, all of the authors have been mathematicians and economists. But Orchard Hayes was a computer system designer and computer programmer. And so now we actually see the participation of somebody who could actually put efficiencies into practice. And this paper introduced something called the product form for the inverse, which I'll describe momentarily. And it for the first time was able to fully exploit the fact that the average variable appears in only a few constraints. And so the matrix of coefficients is mostly zeros. That's called sparsity. And And for the first time, it was able to solve practical problems. So this was actually the paper where the simplex method became practical. Okay? And you can sort of tell it because you find statements like this that begin using the IBM card program calculator when the matrix is needed, then this can be achieved by doing the following. And they still didn't have a real computer, but you see now they're talking about actual equipment and no longer just talking about prospective computational things. And so in this method, we actually write the basis inverse as a product, as a factorization, a product of a bunch of simple matrices. And then we can do the calculations that were needed in the previous example by just multiplying by these simple matrices. And then to update this factorization, we just add one more factor. And that factor is derived from a number that we've already computed in the simplex method. So all I have to show is that these factors are in fact really simple and easy to work with. And here they are. Each one is just an identity matrix, except for some numbers in one column. And some of those may even be zero. So it's very fast to multiply by. And these factors are computed by the well-known means of Gauss-Jordan elimination on the basis matrix. And the Gauss-Jordan elimination emits many different orderings, and you can choose the ordering to promote both sparsity of these factors and stability and numerical stability. So for the first time, there was this flexibility in actually doing the computations, which was essentially being able to do them reliably and quick. And the factors you store only the non-zeros, and of which there are very few. And to update them, as I said, you just add one more factor that's an identity matrix, except for one vector in one column that you already know. And if you get too many factors, then you periodically, every 50 iterations, you can throw them away and redo the Gauss-Jordan elimination. So now, for the first time, linear programming may become practical. And I would describe a practical simplex method like this. The product form of the inverse method was the foundation for how every simplex method has been implemented since then. The only difference is that different factorizations have been used rather than the one that Danzig and Orchard Hayes proposed originally. And they are updated in different ways. So that really was the practical simplex method. So that would seem to be the end of the story, but let's look ahead a bit. Some years later, Danzig published his own textbook on linear programming. It's really a great source book on the subject and all the things that were known up to that point. And he introduced his presentation of the simplex algorithm in that book by saying that it starts with a canonical form, consists of a sequence of pivot operations. Well, this is nothing but the Tableau simplex method. So he actually, even though he had written that paper that I just shown, when it came to write his textbook, he introduced the simplex method by means of tableaus. And he explained that the matrix notation, that's the product form that I described, would obscure the computational aspects. And so he avoided it in the initial presentation and pushed it off to a later chapter. Now, why would anyone favor the Tableau method when it was impractical then and it remained impractical every year since? Well, let's look at it again. The thing about the Tableau method is that it's really simple. There's no linear algebra matrices or inverses. It's basically just a table, and all the computations are essentially in one pivot step. I mean, there are a few other things you need to do at each iteration, picking a row and picking a column, but all the computing is actually done in this one thing that can be done mechanically very easily. And in early years, what was particularly important was that you could set this up really easily for hand calculation back before students had access to computers. And so what happened? Well, textbooks presented this because students could easily do it, and it was easy to describe the calculations without getting into much math. And students learned it, and then some students went on to become professors and wrote their own textbooks and repeated it. And after a while, it became that the Tableau simplex method was sort of everyone's view of what the simplex method really was. And now Orchard still impractical. I don't know how many, no matter how many times it was repeated in textbooks, it remained as impractical as ever. And eventually in 1968, Orchard Hayes wrote his own book. And this reflected his experience in actually implementing the simplex method. It was a detailed account of what really simplex implementations in practical software contained. And he says that he would like it to be found useful as a course text. So he had in mind that this would be a course text instead, that would be a really practical one. Right? But as things turned out, this book was never used as a text. In fact, it's very little known. It's in fact far too detailed for any sort of elementary presentation. And however, as it happened, my introduction to linear programming was as a member of a project led by Orchard Hayes to implement a new linear programming system. And as a result, the textbook that I was given so that I could learn linear programming and get started was this book. And as a result, it happened that I never found this. I was not introduced to the Tableau method and didn't know about it until many years later. And so I always thought of linear programming as being the revised simplex method and involving basis factorizations and not this, and not the Tableau at all. And when I came to teach linear programming, I structured it accordingly. I made up a sort of essential simplex method, which was like the revised method, but I took out the basis factorization. I said, well, we have some way of solving these two linear systems that we need to solve. And it's for a more advanced course to say how you do that by factoring the basis matrix and doing various updates. But if you write it like this, all the essential steps are there. The simplex method involves solving linear systems, choosing and entering and a leaving variable, and computing an update of the basic variables. And that's the one that I used in courses. And in fact, I wrote up notes about this, and those notes are available for use in teaching or just as background, and you can see how to get to them here. So they present it entirely using that approach. Okay. So that's basically the story. And these slides are available for anyone who wants to consult the notation in detail and see how it's done. I say I have a little time left, so I'd like to mention that both Danzig and Orchard Hayes later wrote accounts of their experiences in these early days. Orchard Hayes wrote a lengthy article called History of Mathematical Programming Systems, okay? And talks about better implementations, more powerful computers, and how linear programming software and the computing field grew up together. And he also makes some very interesting curious statements about how computing has essentially reached its zenith, and everything that's going to be accomplished has already been accomplished. It shows the danger of making these predictions. He had become something of a reactionary at that point. And then Danzig also wrote this very interesting reminiscences about the origins of linear programming, very entertaining paper. And it's in this paper that he tells the stories about how the various terms arose. And he summarizes the accomplishments or what linear programming accomplished as systems of linear inequalities, the use of an objective function, and a practical computational method. And I'll leave with this closing thought that it's as important that you can model with the system of linear inequalities and the objective function as it is that you can compute. And Danzig even early on recognized that really the importance of linear programming was being able to do both of those things.